Thank you for inviting me, and thank you for everyone who is here for staying till the end of the day. Oh. Yeah, so I will talk about machine learning for electromagnetic modeling and inverse design. And since this event is called Students of AI, I thought I'd start by quickly introducing myself. So I'm a PhD student. I started last year. I'm in the division of condensed matter and materials theory in the group of Philippe Tassin. I'm also the student representative in MetaPIX, which is a competence center for inverse design in integrated photonics. And in a sentence, my research topic is improving deep learning models for electromagnetism using physics knowledge. So the outline of my talk is that I will first give an introduction about electromagnetics research in general. I will then talk about how we can use neural networks as surrogate models for electromagnetic solvers. Then, after about halfway through, I get to my actual research, and that's a project on resonance-based neural networks, and one on symmetries in deep learning for electromagnetism. And I will end with some outlook and conclusions. So first, what is electromagnetism? Well, the electromagnetic field exists all around us, and it can have ripples, like the surface of water, and those are called electromagnetic waves. And they are responsible for everything from radio waves to light, and they are governed by Maxwell's equations, which have been known for hundreds of years. But even if this is their behavior is well known, electromagnetism is still a very vibrant research field because there are a lot of applications. So people work on communication systems, integrated photonics, where we guide electromagnetic waves in chips to do similar things that electronics does today. And also meta-optics, where we try to create more compact optical elements for sensors. And the common theme here is that everyone is trying to design structures that somehow control electromagnetic waves. So to give a concrete example, I want to explain to you what a meta-surface lens is. So you already know what a normal lens is. It's basically just a piece of glass that is thicker in the middle. And because light travels slowly through glass, the wavefronts will be delayed more if they pass through the middle. And that will cause them to bend and focus into a point, a focal point. And a metasurface lens achieves exactly the same thing, but in a different way. So instead of changing the thickness of the glass, we have tiny structures that, by complex interactions with the light field, also delay the light. And if we were to zoom into the micrometer scale, we would see that the metasurface is made up of these millions of tiny little pillars that are called meta-atoms. And the selling point of this is that while a normal lens is usually quite thick, a metasurface lens is completely flat, maybe only a micron thick, so you can make much thinner lenses. And in fact, if you are able to fabricate metasurface lenses, you don't have to just bend the light to focus to a point. You can do pretty much anything with light. So other cool stuff you can do is, for example, make the metasurface have certain colors. So you can build reflective displays using this. You can do optical computing, where the metasurface basically computes a convolution. So you could integrate like a physical neural network directly into the lens of a camera. And you can even do fun things like use the light to create forces on microscopic structures. So this is a cog with a metasurface on top. And when you shine light on it, it will start to spin. And to be able to do all this cool stuff, we need to answer one question. And that is, how should I pattern the metasurface to get the response that I want? What should the shape of all these millions of tiny pillars be? And that brings us to inverse design. So we can use computers to help us with this. And the way we typically use computers today is solve what I call the Ford problem. So if a human designs one of these pillars, we can feed it into a computer. The computer solves Maxwell's equations and gives us the properties, how it interacts with light. But I, as a human, had to do the difficult step of designing the device. So what we would actually want the computer to do is solve the inverse problem. We as humans want to be able to specify the properties, and then the computer does the hard job of designing the metasurface. So there are many, this is of course a much more difficult problem, and there are many approaches to solve this. And perhaps the simplest is iterative inverse design, which is basically just optimization. So I can start with one, like a guess structure. I use my simulator, I solve Maxwell's equations, I get the properties, and then I can do some mathematical tricks called the adjoint method to calculate the gradient of the design with respect to the properties. And then I do a tiny update of the design, and I repeat that 1,000 times. And then I have a design with the desired properties. So one iteration, one simulation, maybe only takes a minute, so that's fine. But to inverse design, I need to do 1,000 iterations. And that's just for one of these pillars on the metasurface with 1,000,000 pillars. So this quickly becomes computationally intractable. So what would be really nice if we could replace the simulation with a machine learning model, for example, a neural network. Because a neural network can do the simulation in milliseconds instead of minutes. But there is a bottleneck with the neural networks, and that is that you need a lot of training data. And training data in our case is basically pre-simulated geometries. So a neural network is basically like high-dimensional curve fitting, I would say. And for that to work, we then need samples from across the entire design space. So with the problems people usually work with, you maybe need 10 to 100,000 samples from the simulator, and that will give you about 1 to 5% error. And that can take months to compute. And actually this, like the time to generate the training set is the current bottleneck that limits the complexity of the designs that we can create. So my research is trying to solve this problem by using prior knowledge in addition to the data. Basically combine neural networks with Maxwell's equations. So that was the background. So to give a brief recap, we want to do inverse design to create better electromagnetic devices. For inverse design, we need fast forward models. Neural networks are fast, but need a lot of data. So I build physics into the neural networks to make them more data efficient. So the first project I want to talk about is a resonance-based neural network. So first, I will tell you what you usually do in this field, the standard neural network. If we have some device, this is a photonic crystal slab. It's basically a metasurface, but instead of a pillar, there is a hole. If you shine light on it, some will be reflected and some transmitted. And you can plot this as a function of frequency, and it gives you a scattering spectrum. So what you usually do is you input some design parameters that encode the shape of the hole, and the neural network then predicts the transmittance and reflectance at predefined frequencies. But as a physicist, I happen to know that this spectrum cannot have any arbitrary shape. In fact, what we see here is something called a Fano-resonance. So to build this knowledge into the neural network, I use a physics model for the Fano-resonance as a final layer in the neural network. So I describe the spectrum in terms of only its position and its width. So now the neural network only has to predict the parameters of this physics model, which is in some sense a simpler task and probably needs less data. And another kind of bonus that's really cool is that even if I still train it on the science and scattering spectra, the neural network will learn the physics parameters as a latent description that I can then look at. So in that sense, it becomes more interpretable. So here is an example prediction. We trained it, in this case, on the pillars that are represented by like a bitmap. And the points are the training data, and the curves are the neural network predictions. So to see if it's actually more data efficient, we compared it to standard neural networks. And this plot shows the squared error of the neural network predictions as a function of dataset size. The blue curves are the standard neural networks with increasing number of parameters listed in the legend. and our model, which we call the QNM net, is the orange curve. And we were very happy to see that it does in fact need much less data, about 10 times less data for the same error. And as I said, the learned physics is interpretable. So when we could look at these parameters that actually correspond to resonances of the system, we then compare them to direct eigenmode simulations that also give us resonances. And these crosses and dots overlap nicely, which means that the learned physics is actually somehow the correct representation of these spectra. So now moving on to the second project. So this is like a complementary form of physics, where we instead use symmetries, spatial symmetries. So to understand this, I first have to introduce something called scattering parameters. So if we have a general electromagnetic device, I represent it here by a blob, we can define some ports. So these are like ways the electromagnetic waves can interact with the device. We have some incoming amplitudes and some outgoing amplitudes. And the S parameters here, they describe just the linear relation between the amplitudes of the incoming waves and the outgoing waves. So this describes the behavior, and this is like the output of the neural network, S parameters. So the basic observation behind this work is that if we have simulated this blob, I can now just mirror it and create a new blob, and I can infer what the new scattering parameters are without doing an additional simulation. So we applied this idea to a system called, it's called a photonic crystal, similar to what you saw before. And in this case, there are two incoming polarizations, two outgoing polarizations, so that gives a scattering matrix of size 4. This geometry, you can either rotate it 60 degrees or reflect it, and that will give you new designs. So we did the math here and calculated the scattering matrix of these new designs analytically. So that was on like pen and paper work. But the result is then that after simulating just this one geometry, we can create 12 training samples corresponding to the symmetry group generated by this rotation and reflection. And this actually worked. So if we again look at the neural network error as a function of the dataset size, we can see that this kind of augmentation almost gave us a 12 times improvement in data efficiency, about a factor of 10, it looks like, which is probably because the dataset samples are not completely statistically independent. But there is actually another slightly more elegant way to use symmetry. And to explain this, we will look at a simpler problem. So suppose you have this true blue function that you want to learn, but you don't know. You have samples that are these white and black points. And the model you try to fit is a fourth order polynomial that you see up there. A naive fit would look like this. But suppose now that I give you the additional information that the true function is odd. So this is a symmetry of the problem. What we did before is use this rule to generate new data points. So in this example, it will look like this. I get the orange data points for free. But there is actually a more elegant way to use this information, and that would be to simply remove the terms of the polynomial that break the assumption that the function is odd. So instead, we simplify our model, and we don't have to add the additional data. So the analogy for a neural network would be what's called equivariant deep learning. So very smart machine learning people have figured out how to encode these symmetries into the neural network architecture. So you use symmetry to constrain the neural network, and that means that you get less trainable parameters. It's very simplified. It's like we're removing weights of the network. It doesn't work exactly like this, but this gives you sort of a mental model of what's going on. And now the neural network needs less data. It generalizes across transformations. So if we train it on one blob, it immediately knows also the reflected blob. and it will satisfy the symmetries of the problem exactly. So if we compare it again to the other models, we see that it has approximately as well, or maybe a little bit better than augmentation, but it also has these additional benefits of satisfying the symmetries exactly. So to summarize, neural networks can accelerate forward modeling and inverse design, and you can use prior knowledge about the physics to improve these neural networks and make them more data efficient. And as an outlook, so what I presented today was only models solving the forward problem. But people in the field have also developed generative models that directly solve the inverse problem. But so far, there hasn't been much like integration of prior knowledge into these architectures. So I think one step in the field could be to try to develop physics-informed inverse models. And then something else I'm excited about is applications. So people today still kind of think that it takes a minute to do a forward simulation. So, and that kind of limits what you can design. But if you consider that you can now simulate something 10,000 times faster, that unlocks a lot of things like multi-physics modeling, more complex devices, and fabrication robustness. And I think when we really use this opportunity, we will get a lot of cool new technology. So with that, I want to say that I hope if there's anyone in the audience working on electromagnetism, I inspired you to think about machine learning. And perhaps more likely, if there is people from a pure machine learning background, I inspired you to think about electromagnetism as a source of interesting problems. And with that, thank you for listening.